Hello, everyone. Thank you so much for joining us today. We're so excited to have you join us. It is Origin and Cause's 5th annual national tour. This is our second virtual edition, and we hope that next year we can do a little bit more of a hybrid national tour, both in person and virtual. That was our, the first 3 years of our national tour. We did this live in person, going to cities all across the country, and we can't wait to get back to that, and also to actually allow kind of a virtual version as we go coast to coast. Now, in choosing the topic this year, like every year, we try to pick a theme that is relevant based on the claims that we're seeing and what we're seeing in the field. And with so many people at home in the past 18 months and a lot less activity in commercial spaces, we've seen a huge influx in commercial and large losses, while there's been a dip in residential losses. So we thought it was really important for us to really cover complex claims as the volumes are really high. This is something most probably all of you are seeing in a significant increase in. Now, complex claims come in all different shapes and sizes. The only thing that you could actually, what's predictable in complex claims is their unpredictability and the fact that they change and there's so many variables on the go. So sit back, relax, take notes, and welcome to Origin and Cause's 5th annual national tour. So this year, we celebrated our 30-year anniversary and pledged to raise $30,000 for Habitat for Humanity. As part of that effort, we're donating $15 on behalf of each attendee today and next week in the second installment of the national tour. We're honored to make this donation on your behalf and really appreciate you coming out. I want to quickly cover off who Origin and Cause is for folks that haven't used us in the past or have used us every once in a while. So essentially, Origin and Cause we celebrated our 30-year anniversary this year. We're the largest forensic engineering and fire investigation firm in Canada with 17 locations and over 40 forensic experts. You could see those little geo pins on the map as to where we have offices. And we provide services all across major engineering disciplines: fire and explosion, structural engineering, materials engineering, chemical engineering, electrical, mechanical, accident reconstruction, drones, and forensic litigation services. Forensic engineering is a fascinating field, and we're constantly writing articles about things we're encountering in the field that our customers seem to really enjoy reading. We're really passionate about sharing our knowledge with you all, so please make sure to check out our website. If you click on the articles section and the webinar section, you could take a look at a wide range of topics specifically curated for what we're seeing in the field, and specifically focused on training adjusters and lawyers and risk managers. So today we have 3 different presentations. One of them being right now, then we're going to have 2 presenters in that one. We're going to take a 10-minute break and then move on to the next one. So this is the schedule for in Eastern Standard Time. We'd like to take 10-15 minutes of a Q&A at the very end of each of these time slots, and then go to a break. I just wanted to let you guys know that you can submit questions in the Q&A box that you see at the bottom of your Zoom tool. Let me actually share that with you now. Sorry, Dino, I'm going to take back the screen. Quick second here. So you could see this on the footer of your Zoom tool. If you click on Q&A, you'll be able to submit questions. So please submit questions throughout the presentation, and we hope to get to all of them in the Q&A portion of the presentation. We'll be sending each of you completion certificates, hopefully on the tail end of next week. And if you're experiencing any technical difficulties, you can email our team questions to webinar@origin-and-cause.com. All right, Dinu, it's your time to share the screen now.
Okay, thanks, George.
Yeah, no problem. So the first presentation is Forensic Engineering Complex Failure Analysis Investigations. Do you mind advancing the slide, Dinu, please? So our first speaker is Dinu Matei. He has 28 years of industry and academic experience and has conducted over 2,000 forensic investigations. Dinu, his specialties, specifically with a mechanical and materials engineering background, specializes in failure analysis, product liability, commercial and residential plumbing systems and component failures, oil spills, corrosion, materials, metallurgical, and fractography investigations. So without further ado, I'm going to pass off the mic to Dinu.
Good afternoon, everyone, and welcome to our webinar. Today, it will be my pleasure to discuss complex investigations which involve the materials failures. Every material component, appliance, or system is prone to failure. And when it comes to metallic materials, there are only 5 different modes in which they can fail. Fracture, which is the separation of an object or a material in 2 components under the action of a stress. Fatigue is the weakening of the component or material caused by cyclic loading that results in progressive, brittle, and localized damage. Where it's a mechanically induced surface damage that results in the progressive removal of material due to relative motion between that surface and the contacting substances. Corrosion is the dissolution of the material which occurs or consists of oxides buildup, rendering the product useless or leading to failure. All metals and alloys are subject to corrosion. And the 5th failure mode is creep, which is also known as cold flow, which is the permanent deformation that increases with time under constant load or stress. Polymeric materials, they fail in a similar way. Why failures do happen? We see a lot of failures of various components and systems, and although there are only 5 failure modes for metallic materials, there are practically an infinite number of causes for the failure to happen. I split them in several categories, and the first one is service or operating conditions. And I will give examples of investigations that I participated in the past. I start with a unique one, a fire suppression system failure in an automotive paint booth. The environment there was very harsh. There were vibrations, there were corrosive substances. The sprinkler heads were covered with paint. They were subjected to very harsh conditions, and they fell in a short time. An interesting case was the implosion of a sewage pump trunk because the operator mixed the valves, causing this incident. Personal injuries occur due to abuse of tools or appliances. An example is a person who got injured because the tarps, the grommets from a tarp ended up in his eyes. Another negligent person was cutting truck rims with a saw, and when he reached the tire, the saw bounced back, kicking him in the face. A very interesting case, a personal injury which occurred due to operation conditions, was a wheelchair which tipped over while it was ridden by a person. Our investigation determined that it was the radio interference from a nearby radio station with the electrical motor, causing the operator to lose control of the wheelchair. Walkers, we see a lot of such pieces of equipment, which are either improperly designed or improperly maintained, leading to personal injuries. A last example, it's a corrosion of a cooling tower at a hospital. The legs were corroded, and the tower was in imminent danger of collapsing. Improper maintenance. A lot of components need to be properly maintained in order to function properly. A lot of systems need to be maintained in order to function properly. If gears or bearings are not lubricated, they enter into a condition called lubricant starvation, and that could lead to accidents or incidents. For example, wind turbine collapse, crane collapse. If bolts of a wheel are not properly torqued, that wheel can separate from the axle. In a fire suppression system, if the maintenance is not done according to the applicable regulation, that system could fail. In the case of residential fuel oil storage tanks, if they are not maintained according to applicable code, they can fail due to internal corrosion. An interesting case was a fire at a rubber recycling facility where the gears from the conveyor belt were contaminated with the debris and overheated. Manufacturing deficiencies. Also, the majority of manufacturers are trying to produce a product which is defect-free. Sometimes deficiency or defects end up in a product which is available to the consumer. In this category, I include an aluminum ladder which was purchased from a hardware store and caused a permanent injury to a roofer who fell while he was climbing the ladder because the ladder had some deficiencies in its castings. An interesting case, which I will discuss in more detail a little later, involved the collapse of a grind spout. A very interesting case and complex was a commercial pizza oven explosion. First time the oven was used, it simply exploded because the stones were made from improper material. Another interesting case, which was also complex, involved product contamination, in particular chocolate. In long story short, the packaging of the chocolate was not made according to the applicable standards. The manufacturer switched to a different supplier, which provided a package which was substandard. In other words, some of the chemical used to make the box was not according to the standard. A manufacturing deficiency led to another personal injury that involves a paddle board. When the person using the paddle board tried to climb on it, he scratched his chest because the paddle board was not properly finished. In our investigations, we encountered design deficiencies, and a few examples are a video wall collapse at a theater in downtown Toronto because the video panels were not held together properly. The latches holding the panels were substandard. We encounter on a daily basis plumbing components and appliances that have design deficiencies. Design deficiencies could lead to personal injuries, like in a micro saw, which was not provided with a safety pin. So the blade dropped and cut the user's fingers. And another interesting case involving a design deficiency was the collapse of Goldmeyer conveyor anchor bolts, because the load considerations were not taken into consideration properly. The conveyor belt failed. Installation issues are a leading factor for failures. In case of a fire suppression system, if the system is not properly installed and there's no insulation, or there is a condition which favors the formation of cold air spots, that system could freeze during winter. In a water treatment plant, the constructor chose a wrong type of coupling in one of their systems, and that coupling corroded within days, creating significant damage. Luckily, in the next example, nobody got hurt, but it was a spectacular failure involving speakers on a stadium, which failed because they were not properly anchored. We have seen locomotive engine fire because the hydraulic hose was improperly installed. And a big commercial property damage when a pipe on a water treatment plant was prematurely launched in service. And of course, materials and components are subject to wear and tear, especially due to aging. And two examples are a pump used in food industry, which led to tahini paste contamination. The pump was very old, and particles from the rotors were ending up in the product. The other example is also a pump, but that pump was associated with oil. Because it was old, the gaskets were brittle and dry, allowing oil to escape, leading to considerable environmental damage. And there is the act of God. We have been involved in a rowing course marker collapse due to ice impingement, a golf course netting collapse due to ice storm, solar tracker collapse due to windstorms, and we have been involved in fires, oil spills, and floods due to rodents activity. Some people are negligent or recklessness, so their actions could lead to big incidents. People are leaving their homes at the onset of cold season. They don't turn the thermostat up, or they turn the thermostat not high enough. And during winter time, when there's nobody home, the pipes are freezing, leading to floods. Oftentimes, when there is a residential oil storage tank located indoors, it is overfilled because the driver who's delivering oil is not paying attention to the equipment. And we have seen incidents caused for with intent, for insurance fraud, break-in entries, or even revenge. We have seen intentionally flooded homes in order to get money for a free rent project. We have seen orchestrated break-in entries, so people can claim money for personal belongings which were actually not stolen. In a case of revenge, we have seen a gas pipe fitting that was severed with a saw. And we have seen improper use of tools rented from hardware stores where people got hurt and they claimed that the tool was defective. Let me take you through a list of important steps a forensic engineer should follow to successfully complete an investigation. Although each investigation is unique, the basic steps are very much the same. In failure analysis, we say that failure analysis minus analysis equals failure. The basic steps to follow when you are doing a complex investigation is to gather as much background information as possible. Photos from the time of levels, maintenance records, inspection records, repairs, if any, in the past. Try to get an understanding of the circumstances of the event. If possible, interview involves parties like owners, operators, contractors, witnesses. Organize your investigation, prepare it and conduct it thoroughly. Make a list with the task you have to complete, because you might be involved in a different task and you might lose track of what needs to be done. Oftentimes, we are interrupted by homeowners who try to steer us in one direction, or there are some other parties on the site that can make us to forget to run a few tasks. It's important to identify the components of interest for the investigation, document them, condition, environment, relationship with each other. Obtain permission to remove them and document the procedure. It's very important nowadays to prepare a good chain of custody. More and more clients or opposing experts are inquiring about a chain of custody. It is good to prepare a chain of custody from the moment you remove the evidence from a site and until you bring it to the lab. Initially, conduct a preliminary and non-destructive testing and examination. Discuss preliminary findings and further course of action with the client. If a joint destructive examination is required, prepare a testing protocol, circulate it with other parties, and give them the opportunity to make comment and to discuss the testing protocol. Organize the testing and lab examination, analyze the gathered data, and determine the root causes of the failure. In a lot of instances, you have to compare data with applicable standards, code, and regulations. Then we discuss our findings with the client and prepare a formal report if required. Let's review a few complex failure analysis investigations that I was involved, and I hope you'll find them interesting. The first case involves the collapse of a grain silo spout. As you can see in these images, the spout collapsed to the ground and spills grains to the ground. This image was taken by the homeowner shortly after the incident occurred. Luckily, nobody got hurt, although there were people on the property and in the close vicinity of the collapsed structure. Why this is a complex claim? We were asked to determine what could have caused this incident. Was it due to a manufacturing issue? Was it due to an installation issue? Or was an act of God? Because at the time of the incident, it was an ice storm, and apparently some ice accumulated on the structure. The elevator and the great silos were only a few years old, and the failure occurred without a warning. In short, a bucket elevator is used to lift grains to a distributor from which the grains fall through spouts in one or two more silos. So actually those spouts are actually pathways for the grains to be distributed into the silos. By the time we were assigned to this claim, the weather condition changed, the site condition changed. Most of the components that you saw in the previous slides were removed for storage. We could not see their layout on site. It must be noted that oftentimes, for various reasons like safety or economical reasons, the site is cleared quickly, and this will make our work a little more difficult. The structure was unstable and it was difficult to climb it to see its condition on the top. Therefore, we retained the services of industrial climbers, and via radio, I guided them to take important photographs. Back then, the drone technology was not available. However, we have it in our portfolio these days. So in case of a similar incident, we can use our drone to document structures. In this particular images, I noticed a few deficiencies, like crisscrossing cables. And as you can see in the next slide, turnbuckles that are crossing and cables which are rubbing against the top of the lift. The evidence was stored in a shed where we had the opportunity to examine it in the presence of representatives from manufacturer and the installer. The puzzle needed to be solved. The various components needed to be identified and determine how they were installed and what was their relationship with the others. Following this preliminary examination and identification, relevant evidence was collected and brought to our facility for further examination. One item of interest was a component called retarder. The retarder is actually what the name says. It's a specially designed box which slowed down the speed of the grains, just preventing them from being crushed. So the grains are lifted on top of the tower and then through the spouts are going to their respective silos. If the speed of the grains is too high, then the grains could be crushed. Each spout was provided with a retarder, which has two pieces of two pipe sections welded on each side. The spout was also installed on site using welding. So therefore, the retarder has two different welds. One is a manufacturing weld, which was done at the factory, and one weld which was done by the installer on site. It was one of the factory weld that was of interest. You can see by the arrow, this is the factory weld. And this is one of the pipe section at the end of one of the ends of the retarder. Together with the other participants in the examinations, we visually looked at the weld and we marked locations where samples of interest could be cut and used for further examination. Another item of interest was a broken turnbuckle. We wanted to determine whether the turnbuckle was the triggering factor in the failure or it was the effect of the incident. A turnbuckle is, or a stretching screw, is a device for adjusting tension or length of cables. And they are designed to take only longitudinal loads. They are not designed to take lateral loads. And bending of the turnbuckle in the fracture area subjected that the turnbuckle was subjected to lateral loads. We also noted that the threads were crushed in the section where the turnbuckle was in compression. In a fractured component, the mating fracture surfaces are usually mirror images of each other. We cut a small sample from the turnbuckle and we took it to a powerful microscope called scanning electron microscope. Scanning electron microscopes allows examination of components to magnifications up to 30,000 times or even more. We don't need that much magnification in our investigations, but these instruments are capable to go to very high magnifications. And the images obtained under the SEM tells a lot of useful things. In this particular instance, we saw features called cleavage facets, which indicates that the fracture was transgranular. In the left image, we did not see any manufacturing defects that could indicate that the turnbuckle has an issue. Further, we conducted metallurgical evaluation of the turnbuckle. Metallurgical evaluation was done in the longitudinal section, and under optical microscope, we examined the microstructure. And in short, we did not see anything to indicate that turnbuckle was an issue. We did not see any gross metallurgical deficiencies. The microstructure was typical for a steel that is commonly used to make bolts. Chemical analysis indicated again that it's made from a carbon steel, which is also normal for turnbuckle applications. Based on the examination of the turnbuckle and the results obtained, I determined that the turnbuckle was not an issue causing the drain silo spout to collapse. As I mentioned earlier, we selected a few weld samples for examination, and one can see with the naked eye there are some problems here. The red arrow points to a large bead, excessive weld bead actually, and the images taken at a low power microscope shows that the weld did not penetrate throughout the entire wall. So the weld exhibits deficiency called incomplete weld penetration. The fractured weld was taken for examination under scanning electron microscope, and again, relevant features which were not necessarily visible by the naked eye were observed. On the right image, you can see the weld has a lot of pores, and in the left image, the incomplete weld penetration was confirmed. Porosity, not only in welds, but in every material, is an undesirable condition because pores can act as stress concentrators and they can reduce the load carrying capability. Welds are very complex structures, and we analyzed its microstructure, and we found some porosity. Those black speckles are pores in the weld. Following gathering, analyzing the data, I reached the conclusion that the collapse of the spout was the result of manufacturing deficiencies, namely a substandard weld. And also there were other factors adding undesirable stresses to the structure, which are crisscrossing of cables, which was an installation deficiency, and ice buildup due to weather conditions. However, it must be said that these factors acting alone would have not caused the incident. The main contributing factor to the incident was the substandard weld. And as I mentioned earlier, the turnbuckle failure was not a contributing factor, but the result of the failure. As far as I know, the matter was settled favorable to our client, which was the insurance carrier for the silo owner. I would like to discuss another interesting case I was involved, namely the collapse of a tower crane. A tower crane collapsed at a construction site, injuring the crane operator. Luckily, there were no fatalities, but there was significant property and equipment damage. Because there was an injured person, Ministry of Labor was involved, and that made our site access a little more difficult. In this complex investigation, there were multi-parties involved, like the crane owner, the developer, the crane inspector, the Ministry of Labor, and the installer of the crane. what caused the crane to collapse was the failure of a so-called slew ring. Slew ring is a ring which allows the crane to rotate in a horizontal plane. The slew ring is held in place by 48 bolts. And these bolts fractured, which caused the crane to collapse. Several bolts were retrieved from the site for further lab examinations. However, not all the bolts were found. In case of a tower crane incident, it's important to retrieve the crane logos, which includes the inspection, maintenance, and the service. There's very specific requirements on how a tower crane is erected, how is it maintained, and how is it inspected. Some of the bolts retrieved from the site were labeled and were taken to an independent lab for further examination. In examining the fracture surface of the bolts under a low power microscope, I observed that the majority of them exhibit features which are called birch marks, which are always associated with a fatigue mechanism. All the bolts that I examined exhibited these features, indicating that fatigue was the failure mode for these bolts. Fatigue of bolts occurs when they are loose or over tightened. Regardless, it's irrelevant for this particular case because both will indicate improper installation. So when the crane was erected, these bolts were not properly tightened. They were either over tightened or they were too loose. Metallurgical evaluation did not produce any evidence of gross metallurgical deficiencies. Chemical analysis revealed that the bolts were manufactured of the required steel grade and according to the crane manufacturer specification. In conclusion, I said that the collapse of the tower crane was the result of improper installation on site. The bolts securing the slew ring were not properly torqued, and there were no manufacturing deficiencies found in the available fractured bolts. Additional factors that contributed to some degree to the failure was the fact that the incident crane was 30+ years old at the time of the incident, and the life expectancy of a tower crane is estimated to be 25 years. The crane was imported from Germany, where it was no longer certified. The operator did not maintain the required logbooks as per Canadian Standard Association, and the crane operator was an illegal immigrant without working permit in Canada. A third case, which I would like to share with you, involves a car accident with a fatality. The vehicle was driven on a straight stretch of road when all of a sudden it went into the incoming traffic, hitting head first two bikers. One of them died. We were required to examine the components of the vehicle and determine what could have caused the vehicle to lose control and then ending up on an incoming traffic. Our focus was on the tie rod, which is shown in the right image. The tie rod fractured completely, and this condition caused the vehicle to go onto incoming traffic. So the driver had no control with the steering wheel. Tie rods are an essential part of the vehicle steering system. They connect the steering gear to the wheel using a length of rod with a ball in socket and at one end. So practically tie rods are transmitting the movement from the steering wheel to the wheels. In this investigation, it was the car manufacturer involved. It was the service technician who maintained the vehicle. It was the driver, and it was one of the there were the family of the two bikers involved. Having the consent from all the parties involved, we documented the incident tie rod, removed it, and took it for an examination under a scanning electron microscope. Of course, we conducted the mechanical testing and chemical analysis as well. No gross abnormalities were observed. The most important piece of evidence was on the fracture surface itself. These two images taken under the scanning electron microscope shows features called dimples. Dimples are always associated with ductile overload. In other words, the tie rod fractured because of overload. It was subjected to some sort of stress. And it did not fail as the result of a manufacturing defect. There is a saying in material science that the material failed as intended. It's probably hard to get a good understanding of this saying, and I heard from many engineers, why are you saying that? I said, well, the component is designed to withstand a certain stress. Beyond that stress, it will eventually fail. And it will not fail because of manufacturing defect. It will fail because it was subjected to an overload. And this was the case here. So the outcome was that although the driver maintained his innocence and claimed that he did not remember the minutes before the accident, and it was a defect in the vehicle, he was held accountable for the tragedy. So as I mentioned earlier, the tie rod failed as intended. If the tie rod would have been defective, it will fail in a different mode, and there will be significant tails on the fracture surface to indicate that. On the left image, you see those consecutive markings, which are called beach marks, and they are evidence of a progressive failure, an indication that the tie rod will have failed as a result of fatigue. In the middle image, you can see this rock candy appearance of the grains, which is usually associated with hydrogen embrittlement. Hydrogen embrittlement is still becoming brittle due to hydrogen ingression in the microstructure, and it's usually caused by an improper heat treatment. And on the right side image, we'll see those features called cleavage marks, which would indicate that the rod was brittle. So it was not the case. The rod was not showing any evidence of a manufacturing problem. A complex case that I was involved in involved a chair with a welded frame whose failure led to a personal injury. These chairs were installed in a public place, and a parent was sitting on the chair holding his baby over his shoulder. So he was rocking the chair, and all of a sudden the welds sustaining the seat failed, and the baby fell headfirst to the ground. The incident occurred without a warning, and we were asked to examine and to provide an independent engineering opinion on the most probable cause for the incident. We collected the incident chair, and we also collected a few exemplar ones for comparison. Of course, the owner of that place where the incident happened was involved. The manufacturer of the chair was also involved, and the distributor of the chairs was also involved, each sending their own technical expert to participate in the joint examination. As you can see in this image, the design for the seat provided that the seat is supported at the rear using a curved bar welded onto the frame. On the right side, it's a close-up view of a weld on a non-failed chair. This is a design deficiency, in my opinion, because people tend to sway when sitting on chairs, subjecting it to cyclic stresses. And on the incident chair, both welds gave way. And you can see on the right side the collapsed seat, and on the right side the remaining frame with the locations of the failed welds. We documented the frame and the welds, and we took them for examinations under the stereo microscope and later to a scanning electron microscope. The bars with the two failed welds are shown in these images, and one can see that the welds contains large porosity and inclusions. They are undesirable because they act as stress concentrators and they decrease the load carrying capability. One of the weld was taken for examination under scanning electron microscope, which confirmed the presence of large pores and non-metallic inclusions. As I said, these deficiencies are important, are significant, because they act as a stress concentrator and they reduce the load carrying capability of the weld. We also conducted metallurgical evaluation of the weld. The darker constituent in the middle is the actual weld. The lighter constituent in the image is actually the frame and the bar. You can see that the weld is non-uniform and it has some pores in it. My conclusion was that the collapse of the chair and the accident were the results of a design deficiency and manufacturing deficiency. As far as I know, the matter was settled out of court and in favor of the plaintiff. As the result of our investigation, 800 similar chairs from nationwide locations were removed from the service. This concludes my presentation. And if you have any questions, feel free to reach out to me. And if I can, it will be my pleasure to answer.
Thank you so much, Dino. So as we had mentioned before, you can submit your questions in the Q&A box there on your screen. So we have a bunch of questions rolling in. So we're going to answer questions for about 2 minutes so that we can have an 8-minute break before our next presentation. First question, is there an onus on the client to maintain products that can't be seen physically? Example, plumbing valve behind the wall.
Is there a requirement for the owner to maintain? That was the question?
Correct. So plumbing that is behind the wall, is the manufacturer require them to maintain those things?
Most valves used in plumbing systems do not require maintenance, and the building code forbids installation of valves behind walls.
Okay. Interesting. So I imagine if in fact there is a valve, there's usually some sort of opening panel. Is that correct?
The code says it needs to be accessible, put it this way. So okay. Yes, it could be an opening, as you suggested, or the valve could be exposed, either or, okay. As long as you have access to it.
Thank you. Next question. Was the grain silo spout installed by a contractor or by the owners? And was it installed as per manufacturer's specifications?
The silo and the spouts were installed by a specialized contractor, not by the owner and not by the manufacturer. There was one deficiency in one of the spouts. It was longer than permitted.
So it was
Generally,
not installed as per the manufacturer's specifications?
that particular spout was not. And as I mentioned in my slides, there were some deficiencies in the cables and turnbuckles. So the cables were crisscrossing, they were rubbing against a hard surface. And by crisscrossing the turnbuckles, you actually introduce additional stresses in the spout. So in short, no, it was not installed according to manufacturer specifications.
Yes. Okay, thank you. Next question. Were there any comments as to the reasons behind the welding issue that you had presented on?
Say it again, the reasons?
Was there any comments as to the reasons behind there was that welding issue?
I'm not sure I understand.
Was it just poor welding and that's it? It pertains to the kind of the abilities of the welder?
In case of the chair, yes, it was a manufacturing deficiency. The weld was substandard. And the same thing with the weld on the spout.
Okay, understood. Next question. Does Origin and Cause have regular access to an electron microscope?
Yes.
Fantastic. They're asking, you know, if so, what is the cost and ease of booking? So I think we can answer. Yeah, I'm sure we can certainly answer that.
We have a very good relationship with an independent lab, which is equipped with a good scanning electron microscope. And they rent the instrument by the hour. You pay for the instrument and you pay for the technician operating it. So if I remember correctly, minimum charge is $700. And then they go by the hour, which is about $350. So minimum charges for 2 hours, and then you go in 1 hour increments.
Okay. One last question so that we can take a quick break. What was the root cause of the failed tie rod?
It was hard to say. It's possible that the driver hit something, or it was the result of the accident. It's possible that the tie rod failed first, and this caused the driver to lose control. Bottom line was that that rod was not defective. Its fracture led to the accident, but it was not defective. It was subjected to an external stress, which caused it to fracture completely.
Okay. Last question. In your experience, do you see more issues related to installation issues involving code violations or manufacturer design problems?
Where
do you see more issues? Is it installation issues or is it manufacturer design or defects?
That's a good question. I did not keep track, to be honest with you, but I think it's more of an installation issue and also code violations. In sprinkler systems, we see a lot of code violations. In oil spills, we see a lot of code violations.
Yes, great. Thank you so much. All right, so there's a bunch more questions. Thank you all for submitting them. We will try offline to respond to all of your questions. Let's take a 4-minute break and we will resume at the start of the hour with the second half of this presentation. So you can stay online here, just do your thing, and we'll be starting again in 4 minutes. Thank you so much, Dina.
Thank you all.
Eduardo, if you don't mind launching up your screen for us, please.
Can you see the screen, George?
Yes, sir. Thank you so much.
Okay, good.
So folks, we're going to start in 1 minute. All right, let's get the party started. So we're going to continue on with the same topic, complex failure investigations, and we have a new presenter, Eduardo Mari. If you don't mind advancing the screen, Eduardo. So Eduardo Mari has a materials background and graduated with a degree, engineering degree with materials sciences. He has 20 years of engineering field experience and has led over 900 forensic investigations. He is a member of the National Association of Corrosion Engineers and a board member of the Canadian Standards Association of B139. So without further ado, I'll pass off the mic to Eduardo.
Thank you, George, and thank you everyone for joining today. I have an amazing amount of information for you, and hopefully we'll get some great questions at the end and some to follow up in the next few days. As George mentioned, I am an expert in materials engineering, or well, that's what they call me here, an expert. I wanted to tell you a bit of a story which happened this year during a court appearance when an opposing counsel pointed out that since I was a materials engineer, then my area of expertise was on, and I quote, the microstructure and properties of steel, copper, and other metals, unquote. was at that point when I realized that some people do not have a good idea of which areas a materials engineer can specialize in, either by education, formal training, or field experience. In fact, I do have expertise on those areas that a lawyer mentioned in metallurgy, but materials engineering, uh, I would say it's the overarching discipline, which includes polymers, metals, corrosion, fatigue, strength or structural components, chemistry, as well as it branches out into codes, standards, and many more items in the technology world, and chips, microchips, and so on. Today, I have 3 case studies for you. The first one is about a fire sprinkler system, or in particular, the CPVC pipes that are used in these systems, and a joint separation of a pipe and a fitting. An example of materials engineering, as I was mentioning, or an investigation in this, is about the CPVC plastic pipe, which is, it turns to be a complex investigation of which we receive a large number of cases every year. In this one case, I received a call from a client where a CPVC pipe failed in a high-rise residential building. My client wanted me to look into this matter for potential subrogation, and I know that if properly tackled, this can be a home run for subrogation potential. So what I want to do today is explain a little more about this investigation. With that, 101 on our sprinkler system very quickly as well along the presentation. So high-rise residential buildings are typically sprinklered, and in this case, the system failed. The pipe separated. I'll show you a couple pictures later on. What took place there? So basically, the piping in these systems are in a residential building are typically concealed above the ceiling or in the walls. So what was seen by people, what people heard, obviously a large volume of water running through. Eventually, when they came to the area of origin, they see the ceiling collapsed, the pipes separated, and a tremendous amount of water running out of it and flooding everything. So in this one case, the damages included over 40 units, the 2 elevators in the building, the lobby, and some common areas. So you can imagine the damages in this case were massive, and in fact, they exceeded $1 million in damages. With that, also you have the displaced tenants or owners of the condominiums, and obviously those add to the overall costs. One of the key aspects here is that the component, the evidence, was secured. One thing to keep in mind with all sprinkler systems is that they are required to be put back in service very quickly. So whenever you get one of these claims, you have to make sure that somebody goes out and documents them properly. It's best if you have someone who knows what to look for, but if that's not possible the same day or early next day, then at least yourself or another adjuster to document and secure the components, right? So when I go on site in a case like this, I typically inspect the entire sprinkler system and document the conditions and the settings that are that it is set to. Again, attending the site is very, very important because oftentimes the cause of failure is not in the evidence that you secure, so the broken part or the separated piece, but elsewhere in the system or in the building. An example of that can be a system that has an issue with a jockey pump. Jockey pump maintains the pressure in the system, and then whenever the main pump activates, it generates so much pressure that something bursts along the system. So all of those records, all of that information from those on site is relevant and key to determine the root cause of the issue. And again, what I was saying is a complex investigation in sprinkler systems can develop from almost every fire sprinkler component, namely the heads, the metal couplings, steel or polymer piping, and obviously in this case today, the polymer piping failure is what we're going to be looking at. And the particular case we're going to be looking at, the adjuster in this file quickly secured what they believe was pertinent evidence and provided me access to the scene. So here's the separated pipe. You can see this was a 1.5 inch pipe, and obviously it's separated without any warning. This was within the ceiling cavity, so nobody could see it beforehand. And as I was saying before, the repairs of the pipe was completed right away to get the system back into operation and give fire protection to the entire building again. What I received as evidence was the failed pipe only. So as I was saying, that not only the failed component is important, I went to the site in this case, and well, in this particular case, the result of my site examination, I was able to eliminate any other potential causes for this loss. So I knew that the failed joint, the failed pipe joint, was the smoking gun in this investigation. As you can see here, this would be a sample of what a joint looks like, connected to a sprinkler head. What you can see here as a red substance connecting the pipe pieces together is the contact cement or the glue that's used to join the pipes and fittings. And this is one of the major issues that we encounter with systems that use polymer pipes, where the joint sections can separate. A failure like the one I'm showing can be the result of several reasons. One would be improper installation, two, defective solvent cement, or the glue as I mentioned, three, defective pipe or fitting, and four, an excessive internal fluid pressure, in this case, water. And I was saying before, it can be the static pressure from the water, the sprinkler system itself, or an issue with the pumps that can trigger an instantaneous increase in pressure. So as you can see, this can be a complex investigation based on the many possible scenarios that need to be explored. So for a failure that appears simple, you can now see that there may be a large number of parties and experts attending this investigation. And this adds to the complexity as well, because the more parties involved, the more, typically, in my experience, the more that the investigations tend to last, and the more things we have to go through to satisfy all of the experts to reaching a common ground, and even with that, sometimes we don't reach a common ground during the investigations, right? And that's when you see different reports. So in the example above, I am showing a pipe that's separated from the fitting. And amongst other observations, some important issues that we found during the investigation was that the cut end of the pipe was not square, that there was lack or inadequate chamfering or beveling of the pipe end. So these two are critical, and the manufacturer points these out very clearly in their instructions, and for a good reason, right? There was also inadequate application of the contact cement. There was insufficient insertion depth, which is one of the most important steps, as there are several factors that play a role in the strength of the joint based on the how deep it is inserted into the socket of the fitting. So I'm showing here in the picture on the left what we measured as the insertion depth, as well as how the contact cement was applied onto that pipe, and how it didn't make good contact on all the surfaces. So a failure like this one could be the result of a number of reasons. Like I said before, improper installation, defective cement, defective pipe or fitting, or excessive internal fluid pressure. In this investigation, the inspection show that we have to look into the measurements of the components, but also review codes and standards, as well as the manufacturer instructions. And this helps, during this analysis, it helps develop our hypothesis, and which will ultimately lead to a conclusion, or to identify other potential factors that need to be looked into. So based on my analysis, I thought that the cause of failure could be the result of installation issues, or the contact cement being out of specification. So immediately, I contact my client, and then we decide to arrange for a joint inspection with all the other parties. In this case, it was the installer, the pipe and contact cement manufacturer, and the fire protection company who did the actual installation. So during the examination itself, when all the parties are present, right? So in this case, we section the pipe and complete various tests that we try to look for the root cause of failure. Some of those tests included analytical methods such as FTIR, GCMS, which basically help us understand. This is an example of an FTIR test. It basically helps us understand what the material is made of, and not only made of, but what deviations from the standard there can be, or what contaminants can be in the surface, or in this case in particular, whether the contact cement had degraded or was degraded prior to it being put in use. We were able to do that by looking at the blobs of contact cement that were left over on the pipe. Or we can use more complex and specific techniques such as GCMS or gas chromatography, mass spectrometry, to identify specific components and the quantity of those that can be detrimental to the materials, or in this case, the contact cement. In this case, we did not find any components or deviations that were large enough to support a hypothesis of the contact cement being defective. But we did find a lot of issues with the insertion depth, the cutting of the pipe, and all of that together led us to conclude that the installation itself was the contributing factor, or the only contributing factor to the failure, and that the installer did not follow the appropriate procedures, and as such, the improper installation was the cause of these loss. So as you can see, it was a relatively long process to go through all of the potential causes and eliminate those that were not directly relevant, but those that could have had a potential issue or effect were examined in detail so that we could rule them out for sure and leave only one of the causes as the root cause of the failure. I will not be expanding onto this particular new failure mode, which is the failure of CPVC pipes by ESC or environmental stress cracking. But I just want to give you a little bit of a a taste of it, and I'm going to probably be expanding this in a subsequent webinar or an article. Just for you to keep an eye out whenever you see a loss that involves CPVC pipe that has cracks like this. They most likely are related to a couple things. Well, freezing, but freezing can be easily addressed or understood if there is freezing conditions in the building. But if not, then ESC can most likely be the cause, and this requires specialized equipment to prove. And I just wanted for you to keep an eye on it and see what it looks like. And if it serves to open up a conversation for later on, that'd be great as well. I can answer any questions you may have. Finally, I just wanted to mention that the lesson that we learned on this case was that the properly securing the evidence and documenting the chain of custody. In this case, the adjuster did a great job at this. He's quickly, secured all the important components, and they showed to clearly play a good role. Also, important that with the documentation done promptly, the parts were transferred to us and not kept in a in an office space for a period of time. As my colleague Dino mentioned before, more and more the other experts and the lawyers are asking as to where was the evidence stored prior to the evidence being sent to ARCA. So with that, I'm going to be moving on to my second case study, which in this case, it speaks of a boom lift failure with a personal injury. And so I want to show that the contractor in this case, I was working on a boom lift when it suddenly failed, and the bucket fell to the ground, the boom failed, the contractor on the bucket suffered injuries, and in this particular case, the failure, or what we focused on the failure was the the turntable on that boom lift. As I'm showing here, the turntable separated, and the cause for that separation was that all of the bolts in securing it together failed. These two images here are a representation of what that would look like when it was installed. And so I basically was among a group of experts, which included, the lift manufacturer, the lift installer, the bolt manufacturer, for which I was retained on their behalf, the maintenance company, and obviously the plaintiff who suffered the damages. As I mentioned before, the bolts fractured and caused the boom to fail. And in this case, I'm showing you one of the failed bolts and one of the intact bolts from an exemplar or a sister vehicle. And these are some of the other failed bolts. As you can see, some of them look very jagged and rough, and some look more smooth. Going into those that look smooth, we can see that they show some signs which are an indication that fatigue took place there. And in this case, only 5 of the bolts fatigued. We had over 20 bolts, and 5 of those fatigued. And you know, fatigue is a failure, as Dino mentioned in his presentation before, is a failure that typically results from other circumstances. And that can be in the manufacturing of the component, the bolt in this case, the design of the component, the boom lift in this case, say if the loads are not well calculated, in the installation, or in the maintenance of it. And just to give you a quick run by on the fatigue, what you can see here on the left picture is those marks that look like a thumbnail mark, and those are basically indication of a crack that develops in the material over a period of time, and eventually, obviously, the crack is big enough so that the material, or sorry, the component has not enough, or doesn't have enough strength, and it, you know, the crack completes, and the bolt in this case fails by fracture. So, what are the potential causes? Like I mentioned before, me and the other experts in this joint examination were looking at all the potential causes and analyzing them independently to determine whether they played a role in this failure or were just circumstantial causes, right? So one of the things we looked at was improper design, whether the number of bolts was insufficient, or the bolts were too small or not strong enough, whether the bolts were defective, whether the installation was inadequate, or whether the maintenance wasn't done properly. In terms of testing, what we did was initially typical for a metallurgical investigation, which is microscopy, metallography, hardness, tensile test, chemistry. So to get an idea of what these bolts were made of, and whether there were any issues with them internally. So the material strength in a bolt can meet the structural loads, but in this case, so we proved that the material was strong enough to resist the load or the static loads of the component, the boom lift. But in this case, or in this story, there were several other factors that played a role in the design. You can imagine that there are not only static loads because the vehicle drives from one side to another, and therefore those, you know, it carries loads, or some loads are transferred to the boom lift and to the bolts. And then also when the boom lift is in operation, it moves from one side to the other, applying additional loads, not only static loads. So in Canada, the standard for steel construction includes safety considerations for loads, as well as to reduce or eliminating the likelihood of fatigue ever occurring, and those have to be very well taken into consideration whenever designing something like this, especially something that can affect the life of people operating or in the vicinity, right? One of the other things we did, obviously, in the structural analysis, which reviewed all of these, and including the structural loads and the code review. And in my particular analysis, I was able to determine that the bolts met the requirements for their specification, their standard. I also concluded that the design of the boom lift met the minimum structural requirements for its intended loads, but it may have failed to account for cyclical loads caused by the vehicle where it was mounted on or the loads applied during operation. So in short, I was able to prove that the material strength was enough, but may not have been good enough or well within the safety requirements in the structural codes. And then the fatigue in those bolts was likely the result of improper torquing during installation, or that these bolts were not retorqued, or that they were not receiving the proper maintenance that they should have had. So as I mentioned before, that bolts are likely or more likely to fatigue as a result of them being loose than when they are properly torqued. And in this particular case, the installation's instructions did not account for retorquing the bolts, or nor the installer include that in their procedures. Also, to add to that, the maintenance contractor, who was supposed to be doing inspections on a yearly basis, they did not have a chance to complete their annual maintenance on this particular unit because they were running behind due to staff shortages as a result of COVID-19. So as you can see, there were a number of scenarios here that played a role in this fatigue failure of the bolts. And then deciding which one of these was key is obviously the $1,000,000 question, but all of them contributed and all of them played a role in the failure. It's also critical to point out that me and the other experts in this examination were looking at all the potential causes and trying to determine whether they played a role in the failure. But in the end, the torquing or the initial torquing and the retorquing was clear as to all the parties as the physical evidence was showing. And we basically were on the same ground. And I was able to conclude that this was a matter of inadequate installation and a lack of timely maintenance. So after all the hard work and analysis we completed, my client, which was the bolt manufacturer, was let go of the action as we proved that the bolts were not, that the manufacturer and the bolt was not a contributing factor to this cause or to this loss. What we learned in this investigation is that when it comes to material failures, determining the cause of the failure or eliminating other potential causes of failure often requires sophisticated equipment and joint destructive examinations. So for about almost 10 years, I worked in failure investigations for manufacturing companies and aerospace. And oftentimes I used to get clients that came and asked me if I could tell them right away what had happened. And it's interesting because obviously what happened is that the part broke, but to actually find the root cause of that, we have to do some work. In some cases, very detailed work with sophisticated microscopes and techniques to find out the exact cause. Also, it's important to note that liability could affect any other involved parties, or if they're not properly represented. That's clear sometimes when some of the experts, see things in a different way from the rest. So it's good. It's a good idea to have someone there who's representing your side of the story, making sure that all of the stones are turned to look for the right cause. And also that what appears as a simple investigation can easily turn into a very complex one. In any case, I've been talking for about half an hour now. I have a few minutes left. And with that, I have my final case study for you today. It's case study 3, in which I talk about corrosion of stainless steel wires in water connectors. So when you hear water connectors, you probably think of connectors to your faucet or to your toilet, which are relatively small. The amount of water that come out of them is relatively small, but they can also, create a huge amount of damage depending on where they are in the building. But when I look at different connectors like these, I not only focus or not only see the smaller connectors, but I also see the larger ones, like the one here on the right, which is a 6-inch flexible connector in a riser for a high-rise building. And those have the same principles and the same issues that we see with the smaller connectors. So basically, uh, these are basically a hose, either a rubber hose or some other type of internal polymeric hose that has a braided stainless steel wire on the outside. And as you can imagine, depending on the pressures, the inner rubber hose or polymeric hose is not capable of withstanding the internal pressure all by itself. That's why the braided wire material is added on the outside. And those braids, those wire braided material, that's what actually provides the strength for these connectors. And so they can withstand the pressures in service. Now, when we hear that this material is made of stainless steel, we commonly can assume that stainless steel does not rust or corrode. However, we can show different, and that depends on the material composition, the ambient conditions where these uh, connectors are installed, and any other chemicals used during the time that these connectors are in place, right? Here I show one of these connectors that failed. So the braids, so the wire, stainless steel wire braids failed. You can see on the picture at the bottom, there's a slit kind of opening on the rubber, and obviously that's where the water came out. Again, once the metal wires break, there's nothing holding the hose, the rubber hose, and it bulges and perforates. So in this case, I was retained on behalf of the plaintiff, so the unit owner, but I have seen this issue from all angles and represented all different parties that get involved, so the manufacturer, the installer, you name it, right? Typically, there are 3 types of corrosion that affect the wires on a connector like this, and that is general corrosion, which is just surface corrosion, that brown, rusty stuff that we see whenever steel is rusting, corroding. Pitting corrosion, which shows as tiny pits or perforations, small surface perforations in the material. This is much harder to see by visual inspection alone. And it's typical. It typically occurs as a result of some of the chemicals that get in contact with the surface of the wires. And the third one that I see, or it's very common here, is stress corrosion cracking, which shows as cracks that grow into the wires. And I will be showing a little more of these in the next few slides. One thing I want to point out too here is that you don't see a whole lot of rust on this connector. However, there were some rust spots which could have been seen by the naked eye, and as you're gonna see later on, they will turn out to be an interesting talking point in this investigation. So in this case, I was among a group of experts, which included the manufacturer of the water connector, which was from overseas, the wire manufacturer, which was from overseas, the maintenance contractor, the property management, the Canadian supplier, the installer, and the plaintiff itself, the unit owner. Here are some images that I took in the lab. The one on the right is with a scanning electron microscope. As you can see, this one is just about 350 times, some magnifications, but obviously these microscopes can can easily go to 10,000 and 100,000 times to look for very small features that can be the root cause of the failure. On the picture on the left, I'm showing a visual microscope of those braided wires, and as you can see, there are some cracks that are developing. I'm showing them in the picture, sorry, with the arrows there. There are some pits as well, and what we didn't see with the naked eye, there's a lot of rust, a lot of brown, rusty surface deposits, which is a clear indication that the stainless steel is corroding, is rusting away, and it's having some issues. So as I was saying, these failures can present challenges when trying to prove the root cause, even when using the right tools and equipment. However, in cases like this, doing going the whole 9 yards, or going the extra mile, it proves to be fantastic for providing subrogation opportunities in these losses. Here, the cross section. So we mounted and polished these wires to show how the cracks and the pitting progressed inside. And we basically show that there were some fine cracks and pits that weakened the materials and eventually led to the failure. And obviously, as you can see, there's not a whole lot of material loss. So not a whole lot of loss due to surface corrosion. The corrosion itself was just very rapid, very invasive, going into the material itself. And in this case, the root cause or this type of corrosion was stress corrosion cracking aided by pitting. And it points to the hoses or the wires being attacked by chemicals, which caused the breakdown and the starting of the pitting and the stress corrosion cracking. However, there are some times when there are some steps in the manufacturing process that are not done correctly, which makes these wires more susceptible to this type of failure, where some identical wires would not fail, or what looked like an identical fire would not fail. A wire that hasn't been manufactured properly would show, for instance, like I'm showing in this case, it would show some areas where the composition is different, or some improper heat treatment, which will, even though you have the right composition, you have the wrong microstructure, and that's that's easier to make it fail as a result of one of these corrosion types. In this case, the potential causes, as they're listed here, include improper material composition, inadequate heat treatment during manufacturing, the storage of harsh chemicals in the vicinity of the connector, inadequate maintenance or replacement schedule. Then this last point here is very key. You'll quickly see why. That's something that my client, the lawyer in this case, was able to bring the maintenance contractor on board for that. And in my analysis, I was able to show that the wire composition, slightly deviated from what the material specification was supposed to be. and that allowed for localized corrosion to develop much easier. It wasn't completely different from what it should have been, but it was, enough that it would allow for corrosion to start. Also, the wires or the component, the connector showed small but clear signs of corrosion. And in my opinion, this connector could have been inspected and replaced since it was over 10 years old. And one of the things that happened in this case is that the property management, the security and the property management, they could not find the shut-off valve for this particular bathroom. This bathroom was in the common areas of the building, and they had to shut off the water for the entire building. This process took a long time, and therefore a lot of water escaped through the building. So had the property management had better procedures, they could have substantially mitigated the resulting damages. So as you can see, even though the root cause of the failure was a material issue and chemicals that, it can be debatable as to whether they are, acceptable or normally used in bathroom cleaning applications. I believe the manufacturer should account for that. There were other considerations in this file, in this claim, that my client took on and was able to subrogate against those defendants. In my conclusions, the deficient material was the root cause, but the inadequate maintenance was also a contributory factor, and the improperly trained personnel contributed to the extent of damages. What I learned, or what we learned from this file, this investigation, is that when it comes to subrogation involving material failures, identifying other contributory factors is as important as determining the root cause of failure. Remember that the manufacturer was from overseas, so my client in the end explained to me that for him it was very difficult to recover from manufacturer, but at least the share that was attributed to the maintenance contractor and the property management he was able to work with. And obviously identifying all the parties is key, and it oftentimes requires thinking outside the box and gathering the right information early on. That's key, early on in the investigation. With that, I'm conclude my presentation, and I believe George is coming up with some questions.
Yes, thank you so much, Eduardo. So folks, if you don't mind clicking on that Q&A button in your panel, and you can submit questions now. We've got a few questions that are rolling in, so we'll get started. First question, what is the #1 cause of sprinkler system failures? Is it the pipes, the heads, the installation? Is it the manufacturer failures?
That's a great question, and again, we see a very large number of sprinkler failures of all kinds. I personally think that installation is the #1 cause. I think that it would be followed by user error. So the occupant or whoever's working in the building damaging the system, in particular the sprinkler heads themselves, because they're the most sensitive part of the system.
I remember you mentioning one time to me, Eduardo, that manufacturers' defects in sprinkler systems are incredibly improbable. Am I remembering that correct?
Yes, you are. So in that time, in that presentation, I was specifically talking about the likelihood of sprinkler system failures. And, they are very robust systems, and they're very well tested. And because they are manufactured in such a large number, they are typically well tested, proven, and any issues are caught up and fixed quickly. So, yeah, manufacturing issues are typically not as common, but there are, and there are some recalls for sprinkler heads and other components over the years, especially in the last couple of years. There's been a couple out there, uh, but yes, not the number one cause.
Okay, great. Next question. With regards to the boom failure analysis, would you say that another potential cause could be improper use? For example, the overextension of the actual boom itself?
That's an interesting question because I've had an exact case where that happened. Uh, so I'll split this answer in two. I'll answer quickly how that other case, the failure happened, and basically they overextended the boom. Well, you cannot really overextend the boom, but you can try to lift something that's heavier on a position of the boom that you shouldn't. And in that particular case, they were trying to lift a road blockade, a concrete road blockade, and but after an ice storm, and the concrete piece was basically welded onto the concrete or to the asphalt because of all the ice that they had around. So when they tried to lift it, they exceeded the strength of the boom and it fractured. So in that case, all of the bolts failed as a result of an overload. When you see the difference, so the bolts fail as overload, comparing it to the case I presented, where the bolts fail as a result of fatigue, now you can see that the overextending of the boom or having too much of a load on it was not the cause, but rather something else on the bolts. And in this particular case, the bolts were not tightened properly. Hopefully that explains or answers your question.
With respect to failure of braided water lines, what reasonable means can manufacturers take to reduce corrosion risks?
So one thing I've noticed over the years is some manufacturers are better than others at producing these wires. And by that I mean that when you look at the wire outside, you cannot really see any difference. When you look at it like we did in this investigation, we see the composition. But the composition is not everything. After the batch of raw material, raw wire is processed, it has to go through heat treatments. And those heat treatments can be a little more costly or can be done ineffectively. So a good quality control is something that's key to make sure that the wires that come out the door are not only the exact composition that they should be, but they also have the correct microstructure. So quality control and quality control alone would, go the extra mile here. And what I've seen in many of these components is that, perhaps, or in my opinion, the need for reducing cost drives them to, not do things in a proper way. So some manufacturers will be more, will be more specific as to quality control than others. So I think it also speaks of the companies doing the supply, the suppliers here in Canada, that they have to look for reputable companies and not just try to get the cheapest parts they can find.
Yes. Okay, last question before we take a quick break and hop into the next round. How often do you see failures of toilet hose supply lines, and do you see a pattern of the same type or manufacturer? If so, which type do you see the most often?
Yes, I often see those toilet supply lines fail. Um, and so one of the more the more common failures is that plastic coupling that fails. Um, and yeah, there are a number out there. The main issue, and that's something that I discuss with clients whenever we have a chance. The main issue seems to be that they were, you know, yeah, each manufacturer has its own design and objectives during manufacturing. So some of them went to do some thin parts just to save cost and materials. Some of them had bad designs to start with. One of the good things I can I can speak of is that it appears that most of the manufacturers that have parts out in the market today, most of them have had this experience or this bad experience, and they've moved away from those designs and from those materials, so they have more robust components in the market today. So over the next few years, we'll see a decline in the number of failures, or maybe they will shift to something else other than just the plastic coupling failing.
Amazing. Thank you so much, Eduardo, and thank you all for submitting your questions. There's a bunch more questions that we haven't been able to get to. I hope to be able to respond to you guys before the end of the week on all those. So we're going to take a quick break and start again in the next series, the next topic being complex structural claims. We have a nice group of presenters with really, really cool case studies and topics to discuss. So let's take 6 minutes now to break, and then we will be starting again on the hour. Talk to you guys soon.